Hello everyone, this is our workshop project on making a peristaltic pump. We are group 4 from J4CEM 1104F. Let me tell you about our team. We divided the work so that each member led at least one machining process, but we all rotated through the CNC lathe cord and machine handling sessions together, and we all contributed to assembly and non-problem solving.
This video will present an overview of the peristaltic pump, the safety gear and methods we employed, and the steps we took to make the pump, including cutting, lathe, milling, drilling, tapping, and surface finishing. It will also include a discussion of the issues we encountered during fabrication and how we resolved them, as well as a list of our sources. A peristaltic pump moves fluid by using rotating rollers to squeeze a flexible tube. The rollers then push the fluid through the tube without the fluid ever hitting the pump mechanism. This makes it perfect for tasks that need to keep things clean, like dosing medicine, processing food, and moving fluids around in the lab. For our project, we had to make two main parts out of mild steel. Part 1, the pump housing or rotor body, and part 2, the roller bracket. The college gave us mild steel, but we also bought 7 other things like food grade silicone tubing, 626 ZZ deep groove ball bearings, M6 countersunk screws in 3 lengths, M6 manhead screws, M6 nylon lock nut, M6 hex nut, and M6 flat washers.
Safety was our first priority before we did any machining work. Personal safety equipment that we used during the whole project is shown here. For technique, we always make sure the workpiece was securely clamped before beginning a cut. We also check the spindle speed and feed rate against the mild steel material before machining, made sure our hands were out of the way of the cut, and never left a machine running alone. Before each session, we also made our lab instructor to go over the CNC lathe code and how to use the machine.
First, we use the saw to cut our mild steel round bar and flat stock to a rough length. We cut the blank for the pump housing a little bigger than needed so that it could be faced on the left, and we cut the flat bar for the roller bracket to about 47mm in length before cutting it to its final shape.
Then we used the lathe to turn the pump housing. It was cut to length on both ends and the outside diameter was lowered to 50mm. Then the rollers and bracket were put inside a hole that was bored to 45mm wide and 9mm deep. The center hole for the 40mm shaft bore was also turned, and the 21mm body height was faced.
Then we went to the milling machine to shape part 2, the roller bracket. We cut the slot's profile with 2 rounded R7.5mm ends and shaped it until it was 45mm by 30mm. Milling was also used to cut the side slot and find the mounting holes around the wall of the pump box. We drilled the pilot holes after cutting. This included the 3 5mm roller pin holes on part 2, the 6 6mm mounting holes, and 1 8mm clearance hole on part 1, and the pilot holes for our M6 tapered holes. After drilling the holes to the right size, we use a tap wrench to hand tap all M6x1 threaded holes on both part 1 and part 2, while using cutting oil and breaking off every so often to clear chips and keep the tap from breaking.
We couldn't find any sandblasting tools, so we ground both parts by hand to finish the surface. We used a hand-held grinding tool to get rid of the burrs and sharp edges that were left over from milling and drilling. Then we did some finer grinding to get rid of the tool marks on the outside areas before putting them together.
After making both parts, we put the pump together by pressing the 626ZZ bearings onto the roller pins, putting the bracket assembly into the housing ball, and locking it with M6 countersunk screw. Finally, we close the housing with penhead screws, a hex nut, a nylon lock nut, and flat washers. After that, the silicone tube was wrapped around the rollers to finish the pump.
We ran into a number of problems during fabrication. So here are 5 of them and how we solved each one. First, during the lathe process, we experienced excessive vibration or chatter on the mild steel. We solved this by reducing the spindle speed and ensuring the cutting tool was clamped rigidly with minimum overhang. Second, during drilling, the drill bit shifted slightly off center on the pump housing. To overcome this, we made sure to use a center drill first to create an accurate pilot point. Third, when hand tapping the M6 holes, the tap got jammed with metal chips. We resolved it by breaking off the tap half a turn for every full turn to break the chips, and we used plenty of cutting oil. Fourth, the surface finish from conventional milling was initially too rough. We overcame this by using a lighter depth of cut for the final pass to achieve a smoother surface. Fifth, during assembly, the 626ZZ bearings were too tight to press onto the pins by hand. We solved this by using a mechanical press and a tiny drop of lubricant to ease the fit without damaging the parts.
When we think about how we made the thing, there are a few things we could do better next time. Instead of conventional milling, we could use a CNC milling machine for part 2 to get a much higher precision and perfectly accurate R7.5mm rounded ends. Also, having proper sandblasting equipment instead of manual hand grinding would give our final mild steel pump components a much more uniform and professional made surface finish.
Overall, this project taught us how to use a bandsaw, a lathe, a mill to drill, tap and put things together. It also taught us how important planning, tolerances and workshop safety are in real manufacturing.